take a look at the homework first. See if there's any problems or feedback I can give to you. So there's no lecture on Wednesday since all the students are going to a conference trip with me to Denver, and we'll come back on Thursday. So we are in robotics 2 as well. Don't expect me in the office on Thursday. Wait, can I be in the office on Thursday? Yeah, we'll better make it. Oh no, I cannot because we are coming back on at 1 p.m. I guess. Did you look at the flights? I forgot. I think it's 1 p.m. Okay. All right. And there will be a lecture on Friday for this class. That's the plan for this week. And homework 4. It's pretty simple for the first few of them until E. Okay, A, B, C, or D, and E. Let's see. This. I actually learned a little bit from students actually by looking at their drawings. There are 2 ways to do it. So first, I think the PMOS is pretty straightforward. For example, we do AB. Let's see, AB is going to be in series, right, for PMOS. CD, E. Wait, is that correct? Oh yeah. Depends on how do it. Let's do the first one for the first method first. So you got a single transistor E. Okay, you can place E on the top, you can place E in the middle, you can place E at the bottom. But one of the 3 ways wouldn't work for the one-liner stick diagram. Do you know which one? Let's try them out.
When you say one-liner stick diagram, do the polygates have to be aligned for that, or is that just like a
Just one-liner, right? So we're not considering the poly yet.
Ideally, it's better if all the
Sure. Yeah. Let's try all of them and see what's gonna happen. Okay. Because my experience was I always want to put the single transistor on the top. It's always working, but eventually I find out if you put it in the middle, it's actually easier for one-liner diagram. If you put this at the bottom, I tried a few times this morning. I didn't make it work. If you can make it work, let me know. So for the top, it's pretty simple. Which conclusion you want to use for based on our experience for this kind of structure? PMOS, no difference. Okay, so it's going to be straight in parallel. Okay. So 3 in parallel, but it's just to put the 2 transistors in series, treat it as 1 transistor. Okay. So this becomes you got 2 as 1, right? How would you do it? Would you like to skip it like this? And then do this? No. So if you for example, if we connect, so if we treat these two as one, right? So as one, and these two as one, right? How would you like to do it? Like this? Mm-hmm. Remember, 3 transistors in parallel looks like this, right? But we are treating this 2 in series as 1 right now. And then the next to it will be another 2 series transistors. And this is the last one. Okay. So let's see if that works. Okay. So if this is the power line on the top, introduce the power line here and being split into 2 halves, 2 branches, 1, 2, and 3. So that works because you got 3 branches from the top and it merges into 1 here and here. Okay, that's for the PMOS. For NMOS, let's figure out which one is A, B, C, and E first. So this must be E, okay? This can be important because right now we want to determine which one is E. If we use this as E because on the top this is E, and so we probably want to use this one as E. So run through the E, a single transistor first, right? So let's use this one as E, and then 2 in parallel here. How could we do it? 2 in parallel. If we connect it this way, you got the output in the middle, which won't work for it because the two transistors below it connect to this one, not the middle one. So we shouldn't do it that way. What else? Types of different connections you can use for this purpose. I don't think we have done this yet in the past. How would you be able to connect it? You got 2 parallel transistors and then 2 parallel transistors, and they are in series. Actually, one of you guys made it work, make it to work. Okay. We can do this. So we know that this wire is shorted to here, so that's considered as one node. It's being split into 2 branches, 1 and 2. Okay, and then merges here. I'm going to connect these 2 together again, and so they merge it into this node, and eventually goes to here and connect to the ground. It's going to pass LVS if you connect it this way. But if you flip these 2 wires to the bottom, then you're going to have an issue to connect the middle one to the ground because they are all metal one. So I have to put them on the top, which will give you other issues, but we just don't have other ways around, right? Do you? You don't want to route this one below the ground line to here. Keep everything within the 2 rails. That's why we call it rails. Keeps everything in the middle, okay? So now let's take a look at the ABCDs, which one you want to be. So this is definitely E, no problem. Okay, these 2 must be A and B's, right? These 2 must be A and B's. Can we make it to work like this is A, this is B? Can we? No, because A, B are in series over here. So it's either like AB or AB, right? You won't be able to have A on one side and B on the other side, can you? So you have to cross your poly at some point, or you have to use different metal layers to make the connections. So this works electrically, but it's not ideal in terms of layout connections, right? So what if we put E in the middle? I'll just draw the animals. So if we put E in the middle, it becomes this. So we're not changing the PMOS, okay? Just changing the animals structure. So this is method 2. This is method 1. Still use the same PMOS layout on the top. So there will be a line introduced from the top. And you got 2 transistors in parallel, right? And I think we can just do this. Wait, the top is still E. Let's see. Let's make it work first, then we start or reorganize it to align it. So this will be 2 parallel transistors, for example, A and B, okay? And the output merges at this node and goes through E, and you got a parallel transistor again here. So it's pretty simple in terms of layout. We can still not align E to here. But what about other signals? So, for example, we can name, because it's from the top, right, getting split into 2 branches. So there won't be any problem that we name this as A, this as B, okay? There are series transistors from top to bottom, A and B. And so these 2 must be C and D. Okay, can we name these 2 as A and B? No, because this must be E, right? We can probably align one of them, for example, A, name this guy as A, so it's going to be aligned to this one. But the other one has to be B. But on top, you have an E here. What about these 2? These 2 are fine, right? It's going to work. Can we? CD, because it's parallel transistors, so it doesn't really matter. We can just name it as CD or DC, because we have CD on the top, so let's just do a CD here like this. And this is metal 1, so it doesn't matter. We just connect the poly to it, so it's perfectly aligned. So the only issue is E and the B. It's going to cross in the middle. Okay, it's okay. Just introduce the metal 1. Think there will be a way to make it to work. Can we reorganize it to align everything to the top? So it requires a E on the right hand side, right? I don't know yet. Let's just try it. if we have a circuit like this, are we able to align every single line at the poly layer? Would you like to try it really quick on the paper? For if you use this PMOS one-liner layout, okay. Yeah, with this circuit. Mhm. I don't think that's possible. What you think? How to do it? Could you draw it here? That's it. Let me see.
I think the top one. Two parallel and E. That's right. So that works, right? Yeah. Good. Yeah. Cool. So that's a bit different layout on the top. Yeah. So you treat. So what he does is,
Let me just write on the paper so everyone can see it. So instead of keeping these two in parallel like this, you move V in the middle.
Okay.
Okay. So instead of having two parallel, so these two are in series, these two are in series, right? You move one single transistor in parallel with A and B, and then eventually have C and D in series and in parallel with everything afterwards. So it's actually still three parallel transistors, but it's 2, 1, 2 instead of 2, 2, 1.
Okay, so it's 2, right? And 1 which is E, and then 2. Okay. So in that case,
He was able to have E in the middle and have P, A, B, and C, D on the two sides for alignment. Yeah, it's gonna pass NCC. Yeah, nice work on that. Okay. Any questions on this by far?
Did you say it wasn't possible if E was all the way at the bottom?
Yeah, let's try that one as well. What you think?
I did it like that.
Really?
But it doesn't
I could even get a one liner work.
I can draw what I did.
Yeah, let's do it. Yep. That's right.
But I think it's impossible to get switch this and this because it's like
Desires?
apparently doesn't work.
yeah, because every time you do this, you separate A and B
Yeah,
apart, or C and D apart. And if you try and mirror it, it's always going to.
yeah. Well, yeah, no. Yeah. It also. Yeah, you can't flip B and C in any way while keeping these middle three the same.
Um,
I'm not going to do it.
top one. Okay. Just make sure when you are drawing A and B, you make sure the order is correct over here. Okay. So I label as A and B, C and D. Okay. We're looking using this one. So it's also CD and AB. CD, AB. Yeah, that's right. AB, AB. Okay. Cool. So that one's perfect aligned. Let's move to the next one. We got G. Some issues with G. This guy? No, this one. Oh, this is pretty simple. This. Do a De Morgan's law for one time and combine these two terms. This one, De Morgan's law is gonna convert this one into, so combine the sign, combine the bar and change the sign. You're getting A and B or C or D bar. So this becomes the PMOS in parallel, right? A and B in parallel, and then C and D. So if you have single transistors on the top in series with other ones, you prefer to put them on the top. But I think this doesn't matter. But let's still keep the good practice over here. C, D, A, B. So for the NMOSes, A, B, they should be in series and in parallel with C, D, should be pretty straightforward. So got C and D and AB, right? They are in parallel, so they are equivalent. Just do C and D like this. Match. Okay. This is easier, right? Any questions on this so far? Doable? Should we keep this line on the top or at the bottom? Or here? Which one is better? Like, for example, we do it this way. Do this and AB. Which one's better? Wait, is this what we want? No, no, no. Yeah, that's the only way we can do it, right? Wait, no, we have to This is ground actually. Definitely this is better, right? Because we're not expecting any metal 1 on the top because all the signal lines is sending signal in the line, and these are just polys. Okay, there won't be any short circuit. Okay, so that's a solution for that problem. And I think these ones, this is just 1, right? You know, something not plus something is just 1. It's just so fun to look at you guys put so much work on the paper. Yeah. Okay, so don't need a circuit for it. It's directly shorting the circuit to 1. And now let's look at the exam. Let's see. Quizzes exam return. Wait, where's my midterm? Where's my midterm? Geez, I couldn't find my midterm here. Did I put it in here? Don't think if I have a copy of it, but that's all right. You know, since I know where the problems are. I think there are some. Yeah, you shouldn't really lose points from the first one. So it looks like I got a resistor here and 1 power. You didn't even look at it. You think I won't be able to, I won't put this on the midterm or something? Why so many people are losing points on this problem? Is it a 2R? It's a 2R. That's a R. 2R. R. 2R. Is that correct? BL. And I think this is 0 volts and this is 5 volts. 5 volts. We can verify your answer really quick without any calculations, right? I'm just asking you to show the calculation process, but after you find out the final answer, you should verify really quick. Okay. For the digital code for this DAC, it's 110, not 001. Is that not 011? Because this one is contributing 50% of the entire voltage. Why? Because if all these are zeros, okay, you got 2R becomes 1R, and then becomes 2R, and combine you got 1R and 2R. So it's eventually a voltage source over here, and 2R, and ground. So this is just a very simple divider, voltage divider, 5 volts, and that's V out. So for this bit here, this must be the MSB, because whenever it contributes to 1, it contributes 50% of the entire voltage. Are we using 10 volts? 10 volts or 5 volts? I forgot. 5 volts, I think. Yeah. So the digital code for this DAC, for the input of the DAC, is 110, not 011. All right. So you can verify your answer really quick by doing 110, which is 6, right? So 6 over 8 times 5. What's the answer? 0.75? 30 divided by 8. Yes, 0.75 volts. So you know that's the right answer, but when you are doing all the calculations, if it's not leading to that answer, you shouldn't put on the paper, right? We're gonna lose points from that. So how do we show the process of this calculation? You can refer back to all the notes of the the old lectures. But if it's 011, this one is definitely not being considered. It's just a short circuit to ground. So here's a quick question. So for ideal voltage source, so these are all ideal voltage sources. What is the internal resistance of the voltage source? For voltage source is 0. We hope the internal resistance of the voltage source to be 0. So it's not dividing the voltage. It's just providing but not losing any voltage by getting that one divided, right? So when you are modeling a voltage source, if the voltage source has a finite internal resistance, okay, if this is ideal, then you model it with the voltage, and you got a voltage, you got internal resistance over here, you put in series with the voltage source. This should be 0. But in the real world, this won't be 0. This will be something, but still very low for voltage sources. Okay, keep in mind. So that's why whenever it's providing 0 volts, you just short it to ground. It's not. It doesn't have any resistance being contributed to the circuit. So just short it to ground. Then these two combine together as the two parallel resistors. You're getting R, one single R here, and R in series with this R will be 2R. Okay, so you're starting with this part of the circuit with a 2R connect to it. Right? Then you treat anything from here to the rest of the circuit be the load of the circuit. Okay, so it becomes 5 volts, 2R, 2R, and here's the load. So whatever here will be the load. So what's the equivalent circuit for this part? From the load's perspective, when it's looking backward, what is this? What's the equivalent circuit for this guy? So Stephanie's equivalent circuit theory told you you have to remove the load first, okay, and then looking backwards to find out the resistance of this network. That's one single node because they're both ground, right? And short this one, so it becomes two parallel resistors. So RTH becomes 1R, and the voltage out here is 50% of the voltage. So this is basically this, right? So for this part is the same as this one, and this is 1R, and this is 2.5 volts. And you put it back to here, okay? It has another R, and the 2R, and 5 volts and ground. No, we are treating this one as a short circuit, right? For superposition. Now this guy is shorted. We're only considering this voltage source, okay, for superposition. So this is grounded. So circuit becomes this, and this is totally 2R, right? Combine them together, this is 2R. Okay, and then it's dividing this voltage into two halves. Is that correct? Oh yeah, that's right. Because that's the contribution from this voltage source, right? It's 1.25 volts. And the contribution from this one is 2.5 volts. So add them together, it becomes 3.75 volts. Okay? Right. Any questions on this? For the ADC problem, it's a 5-bit ADC, so I have to start with one with 4 trailing zeros instead of 3. Okay, that's 10 volts, so this must be 5 volts. And you're comparing with how much voltage? 6.5? 6.2? Okay, 6.2 volts. Remember the circuit of the comparator, it looks like this. Okay, so not from here, sorry. Through a SAR logic, and eventually it's get a signal and feed it back to the inverting terminal, not the non-inverting. So the non-inverting is the voltage from the sample and hold. So that's the real voltage of the signal. Okay, it's being sampled and held over here. And you keep comparing to that. So this is the constant, which is 6.2 volts, which is given by the problem. Okay, equals 2. So this voltage is being converted by a DAC. All right, so this is a digital signal here. DAC output and being sent to the inverting terminal of the op-amp, the comparator. So at the very beginning, it's 5 volts. 5 volts compared to 6.2 is smaller than that. So what is the output of the comparator at this moment? 1. So you have to put a 1 here, shifting every digit to the right by 1 bit, and you're plugging a 1 here. So this one will be shifted to the right by 1 digit. I've got 3 ones left. So what is this voltage? 7.5. Have to how to calculate it? I see a lot of people struggled on that. So this is 5, right? So what is this? 2.5. Okay, if this is 5, this must be 2.5. So add them together, it becomes 7.5, which is larger than 6.2. So it's outputting a 0. And keep in mind, after this moment, you are plugging in the 0, all the digits here, right, in the middle. So next, you are getting 1 0 1 0 0, right? So this is the original 1 from here. And so this will be 5 added to 1.25. This is 6.25, which is still larger than 6.2. Okay? So it's going to output a 0 to it. This is a 0. Newly added 0 is over here. And that's the original 1. Okay? And this becomes 5.625, which is smaller than 6.2. So it's going to output a 1. The new 1 should be plugged into here, keep in mind. So we're getting 1 0 0 1 1. And this is the original 1. Okay? And now you are getting 5.9375, which is still smaller than that. So next is just plugging a 1 here, which is 1 0 0 1 1. Okay, still the same number. It's not changing anything, which means the final result is still 5.9375 volts as a final result. So 5-bit ADC, you can see it's fairly close to 6.2. If you're getting more number of bits, it'll be even closer. Okay. Right. And now let's take a look at number 3. Problem number 3. There's I think that one is pretty simple. So there's one problem, A, B, C, D, or C, D, E, or A, B, not. So you can simplify this first because you can see this is just A, B, and this has a A, B in it. So you can combine them together to factor out a 1. Leave a 1 in the parentheses, so it becomes AB, 1 or CD. So this will be 1 eventually. So you can cancel CD, cancel out CD. Or you can combine, no, actually not. Just combine this to CD or CDE, not on the top. So this becomes AB or CDE. Okay, and start from here will be very simple. Okay. Another one is A, B, C, or D, E, F, or A, D, E. Do you have a bar on top or not? Forgot. Yes. So how do we combine these? Probably these two both have a D in it. So this becomes A, B, C, or D, E, A, or F. A, B, C in parallel for the PMOSes. AF in series. Oh, D and E. These are AF, wait, am I right? AF should be in parallel actually. No, AF, DE. So it's 3 in parallel and then 3 in parallel. This should be pretty simple, I think. Okay, just do the, let's see. So 3 in parallel like this, and then okay, 3 in parallel, right? So the PMOS is done. This one, these 3 in series, and 2 in series and 2 in parallel. Okay. Okay. Any questions on this? I'm gonna scan this and post it online so you guys can, you know, add this at a later time when you prepare for the final exam in the future. Seems like you guys are doing pretty well on this. Okay. And I think starting from Friday, we'll move forward with a new topic. Okay. I'll have a lab tomorrow. It's a high-speed full adder. We'll see you guys in the lab.